In this video, I'd like to show you a relatively straightforward way to shade or determine what regions in a Venn diagram should be shaded. And that's using what we call a membership table. A membership table just determines whether our the set that we're trying to represent, whether the different regions in our Venn diagram have membership in that set. So we can simplify this. It's very similar to a truth table where, if you've ever seen that before in a digital logic class, a 0 would indicate that an element is a member of that set, and a 0 would indicate that it's not a member of that set, and 1 would indicate that it is a member of that set. So let's take a look at this Venn diagram. It has 4 regions, right? And I'm going to label them this way. We have region 1, which is outside of A and B. We have region 2, which is inside of B, but not inside of A. We have region 3, which is inside of A, but not inside of B. And we have region 4, which is inside of both. So if I represented this in a table with A and B, with columns A and B, and there would typically be more here, but we're just going to represent these 4 regions. So region 1 would mean we're not inside of A and we are not inside of B. So it would be a 0, 0. Okay, not in A, not in B, 0 for set A, 0 for set B. Region 2, we are inside of B, but we're not inside of A. Region 3, we are inside of A, but we are not inside of B. Region 4, we are inside of both. Now check this out. The way I have organized this is such that the rightmost column, the set, you can label those 0, 1, 0, 1. The next column to the left, you can go 0, 0, 1, 1. And that ensures you capture all 4 of those regions. We'll do something similar here for a set with 3 regions, but notice it's going to have, with 3 sets, but it's going to have 8 total regions. So let's start with outside. Okay, we have that region. Then we have just inside of C. I'm doing this order for a particular reason. We have that region. And then we have, we'll have inside of B, but not inside of C or A. And then we'll have an overlap between B and C, but not the region that shares in common with A. Then we have just A. And then we have where A and C overlap. We'll call that region 6. We'll call this region 7, and we'll call this region 8. I guess back up here we could have labeled these rows to correspond to those different regions. And here we can label these rows as well. So notice that region 1, we are not in any of the sets. 0, 0, 0. Here we are inside of C, but we're not inside of these 2 sets. Region 3, we are inside of B, but we're not inside of C, we're not inside of A. Region 4, we are inside of B and C. We're not inside of A. Region 5, we're in A, but not in B, not in C. Region 6, we are in A, we're in C, but we're not in B. Region 7, we are in A and B, but we are not in C. And then finally, here we are in all 3. And these are the 8 different regions. Now, if you look at the rightmost column, once again, it goes 0, 1, 0, 1, alternates between 0s and 1s until we hit 8 rows. The next column, 2 0s, 2 1s, 2 0s, 2 1s, and then 4 0s, 4 1s. And that just helps to quickly build the table for what we're about to do. So, the way we could use this is now, let's say we want to shade this region corresponding to the intersection between A and B complement, union with B. I'm going to draw 2 columns, one for A, one for B. I'm going to label them 0, 0, 1, 0, 1, and then 0, 0, 1, 1. Okay, great. So what I want to do next is ultimately, I want to determine which of these 4 regions are members of this, belong to this. And so in order to build this, I'm first going to start with what's in the parentheses. But anytime I see a complement, I'm going to want a new column for that, just for quick reference. So here's the way I think about it. If I am not inside of B, 0 for that, then I am I'm outside of B, right? I am outside of B. If I'm not inside of B, then I am outside of B. So if I'm not in B, then I am in B complement. If I am in B, then I am not outside of B. So basically, the complement just changes the 0 to a 1 and a 1 to a 0, given that logic. So simple enough. Next, I want to build a column that will allow me to see which of these rows are both inside of A and inside of B complement. So what I want to stare at here is the first and the third columns, and I want to see a 1 in both of those because I want to see which of these rows are in both. Well, we can see that the first two rows are not in both A and B complement. The third is, and the fourth is not. Now what I want to do is I want to union this column with B. So union means you want to be in at least one of the two. So either I want to see a 1 here, or I want to see a 1 here, or I want to see a 1, 1 in both of those. So all I have to do in order to build this is I need to focus now on the second column, because that's B, and I need to focus on the fourth column, and I need to see a 1 in at least one of these two columns. Well, here I see 2 zeros, so I'm not in one or the other. Here I am in B, here I am in A intersect B complement, and here I am in B, and therefore these would be the three regions. So what that means is that as far as my shading goes, this row is a member of the desired set. This row is a member of the desired set, as is this row. Now 0, 1, remember that corresponds to not in A but in B, which would be here. This corresponds to in A but not in B, which is here. And this corresponds to both. So basically what this boiled down to is this whole set could be actually simplified to just A union B. That's all that set really was. Now let's take a look at one with 3 sets, which, this may look relatively uncomfortable, but as soon as we start building this, we'll see that piece by piece it all comes together. So once again, what I'll do here is 0, 1, 0, 1, 0, 1, 0, 1. Next I'll do 0, 0, 1, 1, 0, 0, 1, 1, and then 4 zeros followed by 4 ones. Okay, so I want to focus on building the 2 parentheses first. In order to do that, I want a column for A complement, and I'm going to need a column for C complement. You don't necessarily have to do this. I just think it's easier to make a mistake if you don't. So A complement will basically the zeros will become 1s. So 1, 1, 1, 1, and then these ones will become zeros. Because once again, remember what this means, that if I am in A, then I am not outside of A. And if I am not in A, then I am outside of A. C will be the reverse of this column, or the negation of that column. 1, 0, 1, 0, 1, 0, 1, 0. So that's going to help me because I'm going to build a column for A complement union C. And what I want to see is I want to see a 1 here or a 1 here. So I see that I'm going to have 1, every row has a 1 except, at least 1 1 except here and here. Now every other row is going to have at least a 1 in one of these 2 columns. Okay, great. Now I want to build a column for B union C complement. B union C complement. Okay, so what I want to look at is I'm going to look at this column and this column, and I want to see a 1 in at least one of those. So I see a 1 in C complement. Here I see 2 zeros. Third row I do see a B, so that's good. Here I see a B. Here I see a C complement. Here I don't see a B, I don't see a C complement, so it's not a member of B union C complement. B, C complement, both. B, not C complement, 0. Well, I am almost done, and now I just need to figure out which of these rows are a member of both this and this. Okay, so which of those rows are a member of both of these sets? That's what intersection means. Member of both. Well, I need to see a 1, 1. So that's going to be there. It's going to be there, here, and that's it. So I have 3 rows in which I will see 1s. Okay, let's figure out what these are. So that's going to correspond to, as far as shading goes, 0, 0, 0. So that's everything outside of A, B, and C. all of that region right there. And then also we said we have a 1 here in the third row. Okay, that's 0, 1, 0. That's inside of B, but not inside of A or C. So that's this region here. And then finally, I am going to have a 1 here as well. It's going to be in the fourth row. That's membership inside of B and C, but not overlapping with A. So B and C overlap here, but here overlaps with A as well. So it's going to be just this region. And great, now we've got a perfect shading of this very complicated looking set. And we just do it piecemeal, and it ensures that we get everything collected. Now, beyond just figuring out shadings and what regions things belong to, we could actually use this to also prove different set identities. And by proving it, basically what we would have to do is for something like these De Morgan's laws, which say that if you take the complement of an intersection between A and B, that is the same thing as A complement union B complement. And the way that you could show that this first De Morgan's law is true is you could draw a membership table and then build a column for A intersect B complement. Then in that same truth table, build another column for A complement union B complement. If they produce the same truth table, 1, 1, 1, 0, then you should see a 1, 1, 1, 0 for the right-hand side as well. And if they produce exactly the same values for the corresponding rows, then you know that they are equal and you know that that identity is true.